elastic behavior. So we have two separate sets of solutions which will be defining the system in each of the scenarios. So one is the classical elasticity solution and the other one is the classical plasticity solution. So the second equation, if you see, is P subscript I, which is the normal interface tension, and the sigma RR is the radial stress, which keeps varying with the radius, and the parameters which have been previously defined are substituted to get the stress concentration values in each of the cells. So the right side, you can find the classical plasticity solution. So like I previously said, based on the amount of load that is being applied and the yield stress of the material. So the yield stress of the material is data that can be obtained from any mechanical handbook or a simple Google search. We'll be able to find the yield stress of any material. Uh, so based on all of these properties, the RC value, which is the elastic plastic interface radius, will be changing. So that RC can be determined from the second equation. And when you plug it into the first equation, we'll be getting the sigma RR, or the radial stress value of each and every cell in the plasticity scenario. So now let's move on to the simulation setup. So the CA is basically based on open boundary condition. So we have made it like this so that it can mimic the real life scenario, and it will prevent any artificial constraint at the edges. And whatever we have initialized are the material properties such as Young's modulus, Poisson's ratio. And as far as the neighborhood dynamics are concerned, we are taking both Moore and von Neumann neighborhood. So in the case of hexagonal discretization, Moore neighborhood is basically all the 6 cells that are surrounding the particular cell, because since it's hexagonal discretization, there will be 6 cells, 6 neighboring cells for each cell. The Moore neighborhood will be all the 6, while the von Neumann neighborhood will be alternating 3 cells. So the von Neumann neighborhood has its own share of disadvantages, but it is suitable for certain scenarios. So we have taken that also into consideration. And this is the state vector representation. So each cell's state will be represented by each of these 5 parameters. Whether the cell is cracked or not is the first one. The second one is whether the cell is part of the core or the matrix, because based on that, our expressions of stress is changing. And then the radial stress, which we have computed from the previous formulas, and the area energy, which is also a material property which will be taken from elsewhere, and the strain energy, which can be calculated based upon the stress that we have computed. So this is basically the mathematical expression for the Moore and the von Neumann neighborhood, but that has been discussed previously. And the local rule. So this is the most important part of the study. So initially, when we started, we just chose a neighborhood. So of all the cells that are being considered in the neighborhood, we from the computed stresses, we will be deciding which one has the maximum stress. So whichever cell has the maximum stress, we'll be introducing the crack there. So for each cell with an existing crack, we identify the neighborhood, and the cell with the highest stress is then selected and a crack will be introduced. So this is done for 3 simple reasons. The first one being that the cell with the highest stress location should be relieved first, because then the forces will be redistributed. And then the second one being, when you choose the cell with the highest stress, we'll be choosing the we'll be choosing the part of the material with the uh, weakest point. And the next one is that when we choose the cell with the highest stress, we'll be trying to reduce its overall potential energy, which will guide the entire system towards its more stable state. And then later on in the study, we also decided that another important component that can be included is the area energy. So the area energy is the energy that is that can be provided maximum to the cell for crack propagation. So for the cell to first be cracked, the strain energy must be less than the area energy. So this is because if the strain energy is more than the area energy, then the mode of failure will be much worse than that of a crack, and we will not be able to observe a defined crack. Instead, the material might undergo failure catastrophically. So we introduce another criterion that to even be eligible for further filtering, with further filtering such as the maximum stress condition, we'll first have to choose which cell has its strain energy lesser than the area energy. Later, out of those cells, we'll be considering which cell has the maximum stress. So this is simply the mathematical expression of the rule that I just explained. I'll just summarize it quickly. So we identify the neighboring cells, and then we compare the strain energy and the area energy, and we choose the cell. And then out of those cells that are chosen, we choose which cell has the maximum stress. And from then we introduce the crack in that particular cell. So once the particular cell has been introduced with a crack, we have to relieve its stress and assign zero stress to that particular cell. And then with iterative application of all these rules, we'll be able to trace the crack propagation path. So both realistically as well as in from whatever we have observed from the CA theory, we have seen that there are two modes of crack propagation. So one is penetration through the core, and the other one is deviating and separating the interface. So the penetration of the core happens when the stress concentration of the inclusion is more in comparison to that of the matrix. So this is when the crack is directly penetrating to the inside the core material. So there could be another scenario wherein the crack can deflect and can go around the core instead of penetrating the core. This happens when the stress concentration in the matrix is more in comparison to that of the inclusion. So from here, we'll be just looking at results that have been obtained at when we use different neighborhoods and different elasticity or plasticity scenario. So this is for the elasticity solution. When we are using the Moore neighborhood, we are able to see that the crack is propagating inside the core. And this is the case where the stress in the inclusion is less than that in the matrix. So here we are able to see that the crack is propagating around the core and not through the core. So here we have used one neighborhood. So in generally in mechanical engineering, we always try to reduce the computation time for solving a particular problem. So one neighborhood simply does that. We are able to reduce the computation time because we are only computing for 3 of the 6 cells. However, it has its fair share of disadvantages because, as we can clearly see, that like between the Moore and the Von Neumann neighborhood, the only some of the cells are getting cracked in Von Neumann neighborhood, while that is not the scenario in the Moore neighborhood. And this is elasticity solution when the stress in the inclusion is less than that in the matrix. We are seeing that the crack is getting obstructed at a particular path. It's not moving around when we are considering the Von Neumann neighborhood. This is plasticity solution for both Moore and Von Neumann neighborhood. So here it doesn't really matter whether the stress concentration in the inclusion is more than that in the matrix or not, because the system has reached a critical state, that is a plastic deformation state. The crack is not able to propagate, and in both the scenarios, we are seeing that there is only limited crack propagation, and it stops at the outer rings itself. And this is when we are considering the area energy with the strain energy. So in the first case, we are taking the area energy to be 30 into 10 to the power 8 joules, while in the second scenario, we are considering it to be 15 into 10 to the power 8 joules. So when we are considering a higher area energy, we are seeing that much more number of cells are satisfying the criteria of being having strain energy lesser than area energy. So the crack is propagating further, while when we are considering a lesser area energy, only lesser number of cells are able to satisfy the criterion. So the crack is not able to propagate after a point. In conclusion, what we have done is we have simulated crack propagation in composite materials using elasticity and plasticity principles. And we later on, we also included the strain energy versus area energy comparison. And we decided that, I mean, we were able to see that the higher area energy means wider crack growth and lower area energy means just localized cracks. And the challenges that we are trying to solve here is that often when we use 3D simulation software, we are obviously able to offer realistic stress distribution analysis, but the computation time is increased. And but in CA, we are able to provide efficient algorithms, refined rules, and we are able to define the neighborhood accurately, and we are able to get similar results there as well. So this can enable advanced crack analysis in for practical applications as well in industries like aerospace, automotive, or civil engineering. So um, there we can reduce the computation time drastically, and we can increase the computational efficiency. Thank you.
Thank you, Priyadarshini.
And I would also like to thank the organizers of the summer school and ASCAT 2025. And I would also like to express my sincere gratitude for my guide and professor Gideon Prince, and also to my college NIT Trichy for fostering an excellent educational environment.
Thank you. Lack of time, we will take only one question.
Hello. You have said as a future direction of your study, can you go to that slide, the future direction of study? Yes. So you have said you can decide that you can have the accurate neighborhood definition. What do you mean by that accurate neighborhood definition? What have you thought of? How have you thought of accurate neighborhood definition?
So it's just that it's like a simple comparison between what we can do with the help of CA and the commercial software. So in the commercial software, we are
No,
not
I mean you have already used one name and neighborhood and more neighborhood. What other neighborhood you can think of for
that
that?
that I have to look into. Maybe instead of hexagonal discretization, we can use a much more complex discretization wherein the number of neighbors will be increased. So, like initially, when we thought of starting the study, we thought of a simple 2D cellular automata wherein we use square or rectangular
Okay,
cells.
you can, I mean, think of it and maybe you can have
Thank
some
you.
efficient result.
So you can do it, what you have said, you can do it by just computer simulation also. I mean, or simulation also. Have you checked? You're really getting advantage out of this CA simulation.
I do not have the exact value or the exact computation time because we haven't done any experimental validation with the commercial software. But visibly, we are able to get like results in lesser time.
Okay, thank you. Invite the next presentation, the diabetes prediction enhancement via cellular automata and machine learning. Uh, Deepanshu will present the paper.
Uh, Good afternoon, everyone. I'm Deepanshu Baghel. Uh, I'm I'm a student at DIT Lalpur, and Partha Bishnu is my guide. He's an assistant professor at DIT Lalpur. I will discuss about DIT diabetes prediction in enhancement via cellular automata and machine learning. Sorry, I get little nervous. This is my introduction. Then we will check my main contributions. Then we check methodology, then experiment, data set, evaluation metrics, parameter settings, results analysis, and then conclusion, and then references. This is about my campus, college campus. The diabetes challenges. Diabetes is a widespread chronic condition requiring early diagnosis, where machine learning models are crucial for predictive diagnosis. Traditional machine learning models overlook partial relationships in data. Cellular automata can address this by capturing neighborhood influences. Has some description about cellular automata. So, this is my model framework where we pre-process the data, then apply cellular automata, feature engineering, then we apply machine learning techniques, then evaluate the results. Uh, Here we develop fear-based feature engineering methods, and then we encoded continuous medical feature into discrete list. The steps we discussed in next slide. We created neighborhood risk feature using k nearest neighbors and demonstrate improved uh, predictions accuracy, precision, recall, evaluation matrices. This is the methodology. First, we transform continuous features uh, into discrete with stats low, medium, high. Formula as stats is encoded features. If and T low and T high are the thresholds, then we use uh, k nearest neighbor, uh, calculate equivalent distance uh, between two encoded states, like 5. Then we combine both the data sets, the original one and the enhanced using cellular automata, HRN, MRN, and LRN. Um, I use my Indian diabetes database, 758 records, and which has features. Then calculate evolution matrices by this formula. Selected features. The ML models we use light BGM executes random forest regression. While we compare it with cellular automata enhanced features, uh, we found that the machine learning models perform better with the cellular automata enhanced features. Uh, these are the results of that light BGM without cellular automata and the light BGM with cellular automata. Here we see a slightly improvement with the cellular automata, same as execute, and when we see a random forest, we see a slightly better improvement in accuracy, precision, recorded as one scores, uh, and logistic regression, same to get some better results. This study demonstrated that cellular automata significantly improves binary classification by encoding features into discrete states and integrating neighborhood influences. Um, Peer-based features enhance accuracy, precision, recall, and F1 score. Notable gains where we observe a random forest and logistic regression showcasing and approaching affecting us in improving predictive accuracy of diabetes as we see here. Logistic regression with CM gives the highest accuracy. and as compared to logistic regression without cellular automata. And these are some differences. Thank you.
Thank you.
Sorry,
Deepanshu.
this is first time. So I thought it was my first time I catch this number.
You can understand. Okay. So I'll take one question quickly.
So I didn't have deep knowledge about cellular automata, but in this case, we use totalistic cellular automata, which yes, like नॉर्मल लैंग्वेज में अगर मैं कहूँ तो अगर एक फैमिली में मतलब रिलेशन ऐसे I didn't know.
Okay, yes, thank you. So moving towards the next presentation because it may take more than 15 minutes of time. So the next is use of 5 neighborhood solo automata for pattern classification. Uh, Sukanya Mukherjee. Previously it was 3 neighborhoods, so it will take 15 minutes. Now it is 5 neighborhoods, so maybe 20 will be allowed. The next time 25 minutes for 7 neighborhoods.
Good evening, everyone. My today's talk on use of five neighborhood cellular automata for pattern classification. Myself, Sukanya Mukherjee, and my co-author is Priya Kumari, who is a student of Institute of Engineering and Management, Kolkata. And this is the contribution from our Indian Summer School 2024. Uh, we have taken actually the property of convergence of cellular automation, where we mainly actually concentrate of that kind of cyclic space of CA where all the configurations are attracted to a set of configurations where each of them representing single length cycle, and we call it as fixed point attractors. What is the need of this? Definitely it's theoretically uh, challenging, and it already proven its efficacy in the domain of pattern classification. So different kind of CAs are there, and we need to figure out which CAs are good for pattern classification. Now already work done in the elementary CA, that is two-step five neighborhood. Recently small work done in the domain of three-step three neighborhood also. And we mentioned about strictly single length cycles here. That means we have taken the uniform CA, and where in every for any given length a particular rule generates single length always. So for that actually from there we get the motivation, and we are actually looking for two state five neighborhood cellular automata. Here we are just extending the neighbors. In this case also we use strictly single length cycle CA. Strictly single length cycle CA means, again I'm repeating, just when we are just increasing the CA size, the particular rule always generates single length cycles only. Another factor is that we are considering here multi attractor CA. That means uh, that particular CA always producing more than one cycle. Now question is that here, sorry, question is that more than one cycle means what? It can be exponentially growing. The answer should be no. So here we are looking for stable cyclic behavior. So stable cyclic behavior means what? Even if we increase the number of cells for a given rule, uh, the number of cycles generated should be restricted. And definitely the number of attractors is also moderate. That means here two factors are working. If we just increase the CSI, the cycle structure, I will be explaining that term after a few minutes. Cycle structure should be
approximately same, and the number of cycles should be limited. Here we consider two type of rules, balanced and unbalanced rules. So this is our contribution, that is one is effectiveness of pattern classification by the help of two-state five neighborhoods, strictly single lane cycles. These are just terminologies. All of us know C is an array of cells. Here we are using binary CA, and definitely the state values will be either 0 or 1. And we are considering all the state values together in all cells as configuration. And here we are mainly targeting for five neighborhood architecture, five neighborhood null boundary CA. So how actually we are getting from one configuration to another configuration, where we are taking the five neighborhoods. So as we are taking five neighborhoods, definitely it will stress, so 2 to the power 5, 32 RNPs are there. And this is the representation of rules. Uh, Here we are showing how the configuration, actually how the key evolves from one configuration to the another configuration. This is called as when we are considering, say, uh, one particular configuration and we are moving to the next configuration, that can be only possible by the sequence of RNPs, and we are calling it as RNP sequence. Now the thing is that we have huge number of rules, to the power 32, huge number of rules. How do we select? That's a big question. So, in that case, next point is that we are considering balanced rule and unbalanced rule both. So, what should be in our mind? First of all, there should be the limited number of self-replicating RNA. Why? If we just look at here, if in a if we move from one configuration to another configuration, if the configuration repeats, that means it forms a cycle. How is that possible? If in a sequence every RMP is self-replicating. So if we just think about this, all RMPs are self-replicating, even if it's just for us. So we have to keep on our mind one thing: the number of self-replicating RMPs should be restricted. This is one point. And what type of figure actually what type of architecture we want to get? This is the cyclic space of a particular five neighborhood sphere. Here if we look at here, we can identify actually the number of cycles are limited. So what I told in just the earlier test, if we increase the CSI and if the number of cycles remains same, the number count of cycles remains same, then we can think that should be applicable for our design. Next, I want to just mention about the cycle structure. Cycle structure is what the representation of cycles based on the cycle length. Here, C1 means what? Number of cycles C, and the length of the cycle is 1. So these three things we are keeping in our mind: single length cycles, stable cyclic behavior, and moderate number of self-replicating RNAs. If we start with very simple architecture, all zero rules, in that case, all these things are satisfying. But the problem is that, and if you think, if you just increase the CSI for rule zero, always it will be cyclic behavior remains. The problem is that here the count of cycle is 1, which is never be applicable for pattern classification. Another restriction is that if we have huge number of cycles, then also it is not good for pattern classification. So what we consider, we have to figure out those type of rules where we should have at least two cycles, two single length cycles. And what we have done, actually we have done some experimentation. We add impurities in the loop. Impurities means what? We are just increasing the count of loops. So if we just increase the count of loops, it shows initially all the rules we consider the rules consisting of 0. Then we are just increasing one count, and we are finding out of 32 only one is single and cycle. Then we are increasing the count of rules, and this is the result. But it's very difficult experimentally to do this thing. So we have stopped up to some extent. We have taken 25% once in the rules. This is one way. Another way, what we did first, we consider all the a particular rule is consisting of ones, and then we are increasing the number of zeros. And there also we, for our experimentation, we have done up to 12.5%. In this way, we figured out some collection of rules. These are for unbalanced rules. When we go for balanced rule, then also huge number of rules. We have taken few of them. Now, question is how we are taking those rules which are effective for the pattern classification. Again, I want to tell you here we have done the experimental study where you can see we have experimented for few CSIs for some set of rules and we are finding from this table. Let's consider for 84. If we just look at 84, if we increase the CSI, then also the number of cycles not increasing exponentially. So we have selected this kind of rules and we have selected 150 such rules and we perform the training and testing operation based on this 150 rules. Now, what is the role of pattern classification? What is the actually role of CA in pattern classification? Already it was discussed in earlier session also in first class. So if we consider uh, we have objects from class A and class B, and if we just check here, uh, the first graph actually this one mainly representing more number of patterns from class A or more number of objects from class A, so it is representing class 1 and this also representing class 1 but this one is representing class 2. So in this way we perform it is this particular actually representation of CA mainly extracted by the researcher for the pattern classification problem. Next is how we do the what are the steps. First we have the real data objects, then we go for first of all the encoding, and depending on the attributes either we go for continuous attribute, then we go for sequential encoding, or for categorical attribute we go for one hot encoding. And finally out of actually all number of cycles, all number of attractors, we have to figure out which are useful for a given data set. Even if we consider same CA for different data sets, we may get different type of useful attractors. Useful attractors means uh, uh, in this case actually we need to understand uh, this zero zero is useful. Why? Because some of the patterns come from class A and class B. This is also useful because it is actually from class A, and these attractors also used by the patterns or objects of class A and class B. Next we go for the option of uh, training efficiency. So we can identify from here out of six means in this case out of six, five are from class A, and we are only counting that in this case one out of one and in this case two out of six. So if we find the efficiency, this is the way of finding the efficiency in case of pattern classification based on CA, and this is the 0.86% is the training. Next part is the testing. Previously, when I did work previously, we mainly focus on the testing accuracy. In this work, we actually consider this precision, recall, measure. These are few math metrics are very popular now in machine learning, and we actually in this case we consider these four categories for mainly testing purpose. And here we took some of the rules based on the count of 1 and 2. I highlighted them. You can see I have taken the balance rules. I have taken priority, giving the priority on 1. I have taken the giving the priority on 0 also. And next I want to show you the result part. We have taken three data sets from ML repository, protein, rice, and breast cancer, and just one by one comparison. So here it was showing this tool is giving the best with respect to with respect to this other rules, other five neighborhood rules, and this is actually the comparative analysis. Next result is Next result is for rice data set. Here also you can see this one is the best, and this is the competitive analysis, and the final one is this one, breast cancer. So what I want to say actually, even if we look very carefully, this is just from the experiment I have seen. This tool 1114110 actually performing good in multiple cases. Not for all accuracy metrics, but if you just check here also, you will be getting this 114110 is corresponding. So this is the experimental observation. And yeah, I want just conclude. Before concluding, I wanted to just compare with the existing machine learning algorithms. We have already used here, just like KNN, support vector machine, random forest, net base. So you can see from here, our team is also giving actual results with this in some cases for some metrics also you are getting better results. And yeah, this is the analysis. And for future work, yeah, what we are thinking, here we are using just a uniform script. Then we want to make it again in theory with respect to just putting some non-uniformity in the CO, and we want to see the behavior. So that's all. Thank you.
Thank you, Sukanya. So I'll take
again pattern classification, string computer. What I can see from your slides, this data set that you have chosen is a very small data set. You have to see it clearly. If you change the that number of features, then depending on n the that attractor will they remain same or it will be changing. And the result that you are showing this, if you can recall, if I see it correctly, this is 80%, 88% result, not 90%. Existing, existing machine learning, they are giving more than 90%. No? I think I saw someone giving more.
Sometimes, not always.
Not
This is the result. This what is there.
So you check these results by like
No, I have taken, yeah, you know the fact, some of the work done by my students, okay, some of the taken from paper. I think that is not written. Yes, I can understand your point. Just
because these are very low, so I don't believe this will be too slow.
so it depends on the data set. Here you see, here everything is 90.
Yeah, so
You see here 90. It depends on the data set. What is the quality of the data?
for these rise data set, how many classes are there? Yes, okay. Okay, so only two addresses here you are taking.
Back to the previous slide, I have shown you three attractors.
Three
Okay.
addresses. So
But out of three, two of them taken as class A and one is taken as class B. You have to figure out from these.
but in that figure, if in the data set, 50% belongs to class one particular class and 50% belongs to some other class, how it is handling? In that case, majority huge amount of data going to a particular attractor in that example diagram. So it is an unbalanced data.
The majority voting we are divided into two classes. That's as I actually I don't I cannot rather I could not follow that why you extend the neighborhood. No, the problem is now that you have now large heart space and you may not be able to move around the space. So what may happen that you will be just you will be dropped within a small domain and this is basically what is called of noise. Hmm. Accidentally what you are telling this one you will find in tree neighborhood also. So there are some rules or you know if you have considered the hybrid or like non-uniform. You see that if you consider 255, so without depending, it does not depend on n. Always it will fall in all ones attractor. If it is 254, then all zeros attractor. If you consider 192 and say 207, then there will be a specific pattern you will find which it does not depend on it. So here also maybe the accidentally you have seen this one. So if you increase n, if you change the n, so you will be getting the similar. Okay? But this does not help in classification. So what I'm trying, what my perception is, now you are trying to match the data with the pattern available in this tree or subtree. So in reality, this will not happen. There is a great chance that it will be disappointed. So actually, neighborhood there are lots of options, especially for non-uniform. Here it is very difficult to say. I don't know how you have got this, what is called, rule. Maybe the back calculation. The back, from back calculation you can get, now we start from 4 cells here and manually have, you can try that what is our expectation, what will be the condition diagram. From that we can take the rule. This is one of it. And coincidence that it is basically true for all men. Accidental. So do you find any other rule? Any other rule than this 11 something? That the similar pattern had been taken earlier, even in our lab, when the professor applications here. Basically, there it was the selection is to two-stage fiber so that you can have better accuracy.
Thank you, Sukanya. So now it's time to close that session. Thank you, everyone. So I'll hand over to you.
Now I would request Dr. Richard to present a token of appreciation to our session chair. Thank you, sir. Thank you, ma'am. With that, we conclude the sessions for day one of ASCAT. A heartfelt thank you to all our esteemed speakers and participants for their valuable contributions and engaging discussions throughout the day. We look forward to welcoming you all tomorrow for day two. Thank you.